All right, so on Monday we left off talking about closed form rate of change functions, and specifically we were talking about some notation and some algebra and a whole different variety of things. Today we're going to talk about creation of a bunch of shortcut rules. We're going to do a bunch more on Friday so that over the weekend you'll have the ability to quickly find what is the derivative, what's the rate of change function rule for a variety of things that are presented to you. So I did adjust a couple of due dates on the iMath AS homework. If you looked at it earlier, that's slightly different dates, but again, there's a bunch of homework assignments. They're all open up for you early. There are two of them, one easier, one more challenging, that are just about find the derivative, find the closed form rate of change function for a given function. So like 10, 15 questions just about find the derivative, find the derivative, find the derivative, and that's the end of it. Maybe you want to and plug a number in. But in any case, there are two whole assignments. I forget what numbers say. I think it's like 9 and 10. There's two whole iMath AS assignments that are just that. The first one's easier rules, the ones that we'll have finished by the end of this week. The other one's more challenging rules and more challenging function combinations of things that we'll be covering next week, Monday and Wednesday for the most part. But mostly we're going to wrap up our derivative rule proving discussion on Monday of next week, which will give you a full week plus an extra lecture day. So we'll have from Monday next week, we'll be essentially done, but each day up until the day in class when we're doing your mastery, we'll do a few practice questions just of, can you do this, to make sure you're prepared for a test. Now, in here again, what I described this on Monday, I believe, but in here on Wednesday, Halloween, the 31st, we're going to have first 15 minutes of class just like 25, do a bunch of really quick questions, like 15 minutes to do that, although some of you might be done in about 3, depending on how it goes. So just, take your time. Don't try to finish in 3, but they're the variety of questions that are just strictly following one basic rule type, one basic function type, if that makes any sense to you. I'll give you examples of those once we've gotten through a rule so you know what all this means. And then in recitation, either later that day or Friday or Monday following, so either the 31st, 2nd, or 5th, you're going to be doing a longer portion during your whole recitation where it's longer sorts of questions. Again, it might not take you the whole recitation period, but you'll have the whole period to work on that, with the exception of a few minutes for organization and quick questions. So in any case, that's coming up in a while, but between now and then, we're going to finish up most of the we'll finish up all of the basic rules that we're going to be proving by Monday, and then Monday of next week, and then past that, we'll just be practicing. Now, we're not proving every single function type rule, like not proving how arc secant, I don't think, maybe we will. But yeah, like there are 12 different trig-related functions, regular and inverse, and like 5 other function types that we're dealing with: exponential, logarithmic of 2 varieties, polynomial, constants, and maybe that's 4. But in any case, let's get back to this. Now, just as a note, I think I mentioned this, but wanted to just have this set out there. The rate of change function for any exact accumulation function, or any function really, you can think of it as being an exact accumulation for something or another. But a rate of change function for a given function, if I call that g, is called the derivative of g. So that derivative of, as in derived from, we got this by doing our change in the dependent quantity divided by the change in the independent quantity, imagining a small interval starting at the current value of x and just going forward by h. We can do some algebraic simplification, sometimes some other trickery in order to make that into a nice closed form function that we can imagine h safely getting closer to 0 and not come up with anything undefined most of the time. So those are called derivatives once they're in that closed form. So there's a few different notations, and if you've read the book, there's a whole discussion on the benefits and drawbacks of each of the notations. But one very common notation for the derivative of g, just to use a specific function name, where x is called the independent variable, would look like this. So I could put that on the left side, to name my function, then have the function rule on the right side. And to read this, most people just say d dx or d over dx or the derivative of g of x. And so you can also think of this as kind of an operation sort of structure. But really what this is just a slightly rearranged version of, we had dy over dx. So this is just a dg of x over dx. That looks really awkward. So just putting this over to the side. So it's like d, and this is the name of the dependent variable y, instead of just having a y up there. So if the function's called g, you can write it like this or like that. This structure here with it off to the side is also often used kind of as a, thinking of an operation or a command, like take the derivative with respect to x of the thing that's next. So you can think of this as kind of a compound function. Here's g of x, and then I'm going to take the derivative of that, where derivative is one specific known function called by that d over dx, as opposed to having h of g of x. This is d over dx of g of x. So take the derivative of g of x, where the derivative is done with respect to the independent variable. So for small changes in independent variable x, d over dx g of x gives me the rate of change. All right, so another notation. This one's nice and short, very easy to write. Just uses, it's called, when you read it, most people read this g prime of x, just to say this out loud. This word prime, P-R-I-M-E, doesn't mean something to do with, it's not anything etymological, but just g prime of x, just a little meaning, it's a variation on function g. Specifically, this mark is used to indicate we've done a derivative or found a rate of change of function g. So these mean the same thing. And the way that I can tell that x is the independent variable in this is just because it has that x in the one spot. The other notation, one of the benefits of it, I could take a derivative with respect to another variable that maybe doesn't appear in function g, but appears in some other part. So if I'm taking a derivative of a long complex expression that involves g of x and plus or minus or multiplied by some other things that possibly have other variables, this first notation would be beneficial because I could just specify, well, which of the variables here is considered the independent variable versus which of these other symbols may be parameters or variables that I'm not concerned with changes with respect to. Here's another notation. This is closer to what we've used. This is one that's seen in a lot of textbooks. And you can see this, the fraction part on the right looks very familiar. That's our indicating change in the dependent quantity over change in the independent quantity. The only part of this that's different from how we called this before, first of all, this doesn't have a name. It doesn't look like a function name variety, like it doesn't have a g of x just in the front. We called this r sub g of x. And then we didn't say this expression here, what this is. And this is just a notation that we're not going to use. You'll learn more about limits and their meanings more in depth in later math classes if you take them. But this is essentially saying the same as our h essentially equal to 0. This LIM stands for LIMIT because it's so much shorter. But LIM, limit as h approaches 0 is how that's typically read. The limit as h approaches 0. Oh, but that's essentially what we were doing. We're writing out this expression and then imagining h becoming essentially 0, and can I simplify that to something not involving h anymore under that assumption? So this is just a variation on the way to write that. A little awkward to write because it is awfully long, but again, same sort of idea as what we've used. So what we've used, and again, we've used our expression r sub g of x in two different ways. That same fraction that we saw up above. We used it to mean approximate rate of change with any old value of h. But if we want to make an assumption that h is going to be essentially 0 or choose exceptionally small values of h, then we can say that this r sub g of x is an exact rate of change function. So derivatives are exact, not approximate, rate of change functions. So we only want to use the phrase derivative if we're talking about this expression with h essentially 0. These other notations, this is used when, they're formed the same way, regardless of what the notation is used to represent them. To find a derivative, it uses the same tools, finding the ratio of changes in the dependent and independent variables as we look over smaller and smaller intervals of the independent variable. So these are all formed the same way. It's just, what do I call this, or how do I express what I've done? So this is a more open form expression, like this one is. It explains what's being done. These are just short notations for those, but they mean having done the same thing. They're not something entirely different. Just with this, again, we've used it two ways, with small h and with not specific h. So it's either just some sort of rate of change or an exact rate of change if we imagine h exceptionally small or h essentially 0. So in any case, regardless of what notation's used, just keep in mind it's always talking about this rate of change of whatever the function name is, g, with respect to x, or the rate of change of g of x, or whatever the dependent variable name is. Sometimes you're not given a dependent variable name, and so people just use the function name in place of that. It's not ideal, but if you don't have anything short to say about it, you'll see that done, like I just said. The rate of change of g of x with respect to x would be more appropriate because g of x is the dependent variable. G is just the function relationship. So I'm going to say derivatives for constant functions. Again, that just means the rate of change for constant functions. So let's take a look at what happens with constant functions. We're going to develop some shortcut rules. So if I have a constant function, that means I can think of an accumulation, so-called function, where nothing's actually accumulating. Like going back to the bathtub example, bathtub where the water level is staying the same all the time. So what's the rate of change of a function if nothing's changing? Yeah, 0, right? So if I have any function of the form like y equals c, or f of x equals c, f of x equals 7, f of x equals -4, f of x equals 80,000,000.2, whatever it is. If I have f of x equals, or whatever the name of the function is, with respect to x equals just a number, we can use we can derive this. It's not magic, and it's not just, it is kind of common sense based on the definitions of our words, but thinking about how our derivative rule, our rate of change trusty function, f of x plus h minus f of x over h, and then imagine h becoming small, we can create that rule from scratch algebraically without having to rely on common sense or sentences. So if f of x equals c, what's f of x plus h? Well, to find f of x plus h, we normally replace the x expression in the function rule with an x plus h. As there is no x, there's not really anything to replace. So if I'm trying to write out this expression to find the rate of change of this function f of x plus h, f of anything is going to be c. F of x plus h is c, f of x is c, it's always c. So if I subtract this, I get 0 over h, which I can imagine h being anything I want, but a fraction with 0 on top is 0. So 0 over 5, 0 over 0.1, 0 over anything, those are all equal to 0. So as long as h isn't equal to 0, this is 0. Like we were saying, we can't actually have h be equal to 0. We can only have it be extremely close to 0, exceptionally close to 0, because the division by 0 isn't defined. But 0 over something that isn't 0 is equal to 0. So, short version of this, if I have a function that's a constant, its rate of change is 0, which is what we just said without having to do algebra. But it can be proven using the same rule that we apply to everything else. It's not an exception to a rule. The rate of change of a constant is 0, because a constant, thinking about the reason we use that word, isn't changing. So short way to write this, if f of x is c, r sub f of x is 0. Or we could use some of our other notations that we were talking about. I could say the derivative of a number like 5. So maybe f of x is 5. The derivative of 5 is 0. Or if I had g of x equals negative 13, then using that prime notation, g prime of x is 0. G of x is a constant function, so its derivative is 0. One of the benefits of this notation is that you don't have to have a function name. You can think about just an individual term without it being assigned to a dependent variable. So an expression, some sort of computation, or in this case, not a computation, just the number 5, regardless of what this might be the rule for, like y equals 5, or h of x equals 5, or whatever it might be, if I think about take the derivative of this function rule, that's just simply the number 5 in this case, that function rule's rate of change, regardless of what that dependent variable may be called, with respect to x, which doesn't even appear here, this is 0. No matter how much I change x, 5 doesn't change. All right, so, oops, that's not what I wanted. So let's talk about a different variety of function that's slightly more interesting than constant functions. Let's talk about functions that are, well, not a specific type of function, but just in general. Let's say I have two functions and I know how they're related. One's a multiple of the other. So I see this phrase constant again, but it's constant multiple. Meaning, for example, let's say at every moment in time, John has traveled 5 times as far as Mary. So maybe at 2 p.m., John's traveled, let's see, 10 miles and Mary's traveled 2. I don't know where they are, but I know how far they've traveled. If I know how far they've traveled, that sounds like a net accumulation. That sounds good. But if his net accumulation is always 5 times as much as hers, if his distance function, the position function, how far you've traveled function, whatever you want to say, always has values that are 5 times as large as what hers are, how could you describe his speed relative to hers? Yeah, 5 times as much. Like in the next hour, he would have to travel 5 times as far as she does to keep that relationship. So his speed must be 5 times as much. So what that means is if I have these two functions, I'll just call them f and g. F is John's distance traveled after x hours, and g of x is Mary's total distance traveled after x hours. And I know that his is always 5 times hers based on the description in black up here. So f is 5 times g for any value of x. So if I know this relationship, then I know that his speed is also 5 times her speed. So I can just take this expression and say, oh, well, because of this relationship between f, because f is a constant multiple of g, f is 5 times g, then the rate of change of f is 5 times the rate of change of g. Well, that's interesting to know. That doesn't help us with the specifics. Well, how do I find his speed? If it's a constant, I would know what that is, but that would be a really boring question. We haven't talked about a whole lot of specific functions f and g whose rate of change functions we already know. We have talked about one, so let me just use that as a quick example. One that was simple, if you remember, we talked about f of x equals x squared. The length of a side of a square being x and the area x squared. We found out that the rate of change of function f was 2x. So r sub f of x is 2x. Now what if I had some other function? I'm going to call it k. What if k of x was 17x squared? It's a constant multiple of function f. Well, it's a constant multiple of function f. That means their rate of changes are constant multiples also. So this no longer has anything to do with the area of a square with side length x, because 17 doesn't play into that. But whatever this might represent, this f of x statement is true. And if k is a multiple of f, k of x is 17 times f of x, then k of x's derivative, r sub k of x, has to be 17 times this, 17 times 2x, otherwise known as 34x. There's no need to keep those separate. I can simplify that. But the idea is, if I know how to find the rate of change of a simpler looking function, if I suddenly have a constant coefficient multiplied on, then I know how to find the rate of change for that as well. Just multiply that constant coefficient, that constant multiple, multiply that onto the rate of change of the rest of it. So, for instance, we actually dealt with this entirely already. If you remember the sphere question, let me clear this. We had the volume of a sphere was 4/3 pi x cubed if the radius was x, and we decided that the rate of change of function v with respect to x, it came out to be, in simplified form, 4 pi x squared. But what we'd worked out was we had this factor of 4/3 pi off to the side, and from the fraction with all the h's that we were reducing out, we had a 3 and an x squared. That reduced to 4 pi x squared just by combining these coefficients. But if you can see, x cubed on its own corresponds to a rate of change of 3x squared. And then there's this constant multiple that appears that we get to multiply back on, and we end up with the same result. That's not how we derived it before. We didn't talk about any constant multiple properties and pull out the coefficient and just deal with the x's. But that's how this works. If x is the part that's changing, when I'm talking about rate of change, constant coefficients, constant multiples like that, aren't changing. They scale everything up. And graphically speaking, this is something that I bet you've talked about in as far back as algebra classes. For instance, if you were asked about parabolas y equals x squared versus a parabola y equals 5x squared, what you probably talked about in earlier algebra classes is, oh, that coefficient of 5 makes it steeper, makes it stretch by a factor of 5. Well, guess what that does to the rates of change of y with respect to x? It makes it greater by a factor of 5. It's exactly the same thing. You were learning calculus back in algebra, and you probably didn't even realize it. But it's the same sorts of things. And slopes of lines also. You know that putting a different coefficient on x and a y equals mx plus b can make it steeper or can make it less steep. That's just altering the ratio of change in y to change in x, or the dependent to independent quantities changes in that line. All those coefficients have done the same thing over time, but maybe you just didn't use these same words. Probably not, especially back in algebra the first time. Haven't talked about what that relationship is, but let me use some notation here. If I wanted the derivative of this y, another way that this is written, since this is just a single variable instead of function notation, lots of times this d over dx style notation, the y is put on the top as opposed to off to the side because it's nice and short. And then that looks just like what we talked about before. The ratio of changes in y to changes in x is 2x. Whereas in this parabola, if I graph it, thinking about the shape of it, I know it gets steeper, but it's steeper by a factor of 5. So 5 times 2x, otherwise known as 10x. So in any case, this is just our constant multiple rule. If you have a coefficient, is how it's seen most of the time. If you have a coefficient or just a number, a constant, that's multiplied onto something whose derivative you already know, you don't need a new rule for that. You just need to multiply that constant back onto what you know as the derivative or rate of change of the rest of the function, the other factors. So, all right. So again, this is, don't forget what we're doing when we're talking about these shortcuts. Rate of change of f with respect to x is 5 times the rate of change of g with respect to x. You can say this much more quickly if you say the derivative of f is 5 times the derivative of g, but just don't forget what derivative means. It means the rate of change, the thing that we've been working on since the beginning of the semester, because again, if I wanted to evaluate this someplace, I'd be talking about the essentially constant rate of change in a moment around a particular x value. And that gives us ratios of changes for small changes in x in that moment. All right, but let's take a look at a different question. So here we've got in general, doesn't have to do with 5 in particular. For any constant multiple of a function whose derivative we can express, I know that the derivative of the multiplied version is just different by that same constant multiple. So what if I have pieces added together? So if I have a function g and a function f, whose terms are added, like x squared plus 4/3 pi x cubed. I know how to find the derivatives of those separately. We did this carefully last week. Well, they're kind of a mess, but whatever those functions might be, if I just think about this premise in general, two functions of any sort. Thinking about our trusty function, if I wanted to find the rate of change of function k, I'd need k of x plus h minus k of x all over h, and then imagine h becoming smaller. So just as a way to set this up, if I want to find what do I do if I have multiple functions added together, if I have multiple terms, each of which could be considered its own function. So, well, if I have k of x plus h, that would involve subbing x plus h into both of these spots. K of x would just be the original function as it's listed. And without even knowing what function f or function g are, which makes this more general, applies to all cases, I can write this expression. So that's got some familiar looking pieces in it. If I had f of x plus h minus f of x, all in its own fraction over h, that would be the derivative of f, or the rate of change for function f. And they're not together right now, and there's this g stuff in the way, but this is fractions. I've got this large fraction with addition and subtraction in the numerator all over a denominator of h. I can rearrange that. There's no problem with this. And I can even split it into a couple of fractions if I want. Algebra says that I can subtract, I can change the order of addition and subtraction as long as I'm careful with keeping the negatives, the subtractions, in front of the terms that they go to. So that's in front of the plain f of x and g of x terms. Those should both have subtraction in front of them. So I can rearrange those terms, commutative property, or associative property, or a combination of their four, I guess. And because of how fractions are added, if I have a bunch of stuff added in the numerator of a fraction, I can split it into two fractions. If I were supposed to be adding these, it would look exactly like that by the time I'm done. But you can see from this two-fraction version here, the first fraction is precisely the rate of change of function f. That's its expression, as we've learned, or the derivative of f. And the second fraction is the same for g. So if I have two terms, each of which could be considered their own functions, and you can see this could easily extend to 3 terms, 4 terms, 5 terms, however many terms. If I have terms that are added or subtracted, because I could always write subtraction as plus a negative, and a negative is just a coefficient of -1, and we know how coefficients work. So any number of functions, added or subtracted, any number of terms to an expression that are put together to create a more compound function. To find the rate of change for that compound function that has multiple pieces, multiple terms that might have positive or negative coefficients on them. We can find the derivative by, essentially, if you can see, just term by term, find the rate of change of each individual piece of that sum. So we can do that. Meaning, okay, so we've got our 3 basic rules, and we've talked about this is a constant as a type of function. The other two are kind of variations on functions that we know. We don't have a lot of functions that we know, however, but just to put those up there, let's say I had something like k of x equals 2x squared plus 5x minus 6. Now, we haven't thoroughly talked about all of this stuff before. We're going to make kind of a leap of thinking here. But if I wanted to know the derivative of function k, let me use this prime notation this time. This first term is like our square that we dealt with, the square area function. Did I change it? Okay. So I know that the derivative of, or the rate of change of the x squared part of that was 2x. And then we've got this coefficient of 2, according to our coefficient rule, our constant multiple rule. This 2 in front corresponds to a 2 in front, a multiplied on factor in the derivative as well. Now, this minus 6, I can think of this as plus a negative. So I can just imagine plus if I want to. But what's the rate of change of, and I'll get back to the middle term in a second, what's the rate of change of this negative 6? 0. It's a constant term. It's a constant function if it were sitting on its own. I can imagine this f of x plus g of x plus h of x or something, just sums of as many functions as you want. But yeah, this negative 6 here on the end, plus a negative 6 or minus 6, however you want to think of it, has a derivative of 0. It's a constant. Now, if I have a function f of x equals 5x. That's a linear function, or representing constant rate of change. What is the constant rate of change for this term, 5x? Yeah, it's just 5, right? It's a linear function. You've talked about rates of change representing, angles of things. If this were just on its own, it would be a linear function with a slope of 5, or a linear function with a constant rate of change of 5, y equals mx. And so if I want the rate of change of just this term, because of our last rule here, whether or not there's other things added onto it, I can find the rate of change of this piece on its own, and the derivative of that piece, or the rate of change of that piece on its own, is positive 5. So to write this kind of like a more advanced math person, I will simplify this a little bit. K prime of x is, instead of 2 times 2x plus 5 plus 0, I'll just write 4x plus 5. So without having to go through looking at k of x as its own function and starting from scratch, although we can, k of x plus h minus k of x all over h, we could write out that expression, subtract some like terms that arise, do some factoring. This would have some expansion to do, factor out an h, and reducing. We can get to this by just relating this k of x to rules that we've already dealt with and examples that we've already seen. So we've got this one, which particularly was related to the area of a square that we worked out earlier. This that's related to linear functions and constant rate of change. And then we have a constant, which we just talked about constants particularly. And then we've got coefficient here, or a constant multiple. And I've got a sum of 3 terms, which, although this only addresses 2, you can see that would work just as well if I had 3 or 4 or 17 functions added together. So I want to talk more about that x squared, because really we're kind of out of things to talk about unless we talk about more types of functions. We talked about x squared and 4/3 pi x cubed in specific, and then constant functions, and well, linear functions aren't that bad. But what if I have other power functions, not just x squared, or an x to the first power, which is easy, or an x to the 0 power, if you want to imagine, which would be a constant. But what if I have x to an n power, any power function? Power functions are ones where I have my independent variable raised to a numerical power. They could have coefficients on them, and they're still called power functions. If you add a bunch of terms, you call them polynomials or something else instead. But in any case, thinking about single terms, because I know if I have multiple terms, I can always use another derivative rule. So we'll just concern ourselves with powers of x. And we worked out this when we were dealing with area of a square, x plus h squared. And GC can do that for us as well if you have to expand something that looks like x plus h raised to a power. And we did that with x plus h cubed when we were talking about the sphere, because it gets quite annoying to distribute x plus h times x plus h do all that, and then multiply on another x plus h, and if you had to do that 4 or 5 or 20 times, it would take a long time. There's binomial theorem that tells us about this, if that's something that you learned about in maybe an Algebra 2 class or a pre-calc trig class. If you learned about binomial theorem and binomial expansions, there's shortcuts for how to expand these, and in general it looks like, well, there's nice patterns. But the numbers near the ends of this, if we put them in increasing or decreasing order of powers of x, or opposite for the powers of h that arise, there's nice patterns. Like in x squared, I have x squared plus 2xh plus h squared. And at x plus h to the third power, that second term starts with a 3, because there were 3 different ways among all the different binomial factors to pick out 2 x's and an h. Or there's 4 ways to pick out 3 x's and an h when I have 4 factors of this, and they all end up being like terms that we combine. So if there's n factors of x plus h, that second term here is n x to the n minus 1 and so forth. But there's just nice patterns in these. So there's a lot of messy terms in between. Then there's ways that we can explain the coefficients with combinations, if that sounds like something familiar, like factorial expressions. But again, save that for another class if you want to learn more about the binomial theorem and how it works and why. But in any case, just visually speaking, there's a nice pattern here. And we're just going to do this kind of as an informal proof. But if I wanted to find the derivative of f of x equals x to the n, I'd need f of x plus h, which would look something like this last rule here, minus f of x all over h, and then imagine h to become essentially 0. So that's if n is an integer, or a positive number of some sort, whole number. 0 is boring. If I've got whole numbers here, this works out the same. Now there are other proofs for n not equal to integers, although it does involve other strategies, logarithms and such. But I'll talk about that later. So I'd need this expression here would give me my rate of change for function f, or my derivative of function f, when it's strictly x raised to a numerical power. And I can, if n is a whole number like this, I can expand this first part. I'm just going to write it like before, some of the terms showing, because we know there's a nice pattern. I threw in a couple extras there. But powers of x decreasing, powers of h increasing as we go throughout one at a time. That x plus h to the n is the messy part of this. But I know I can subtract this x to the n and this minus x to the n at the very end. So the first term of this expansion minus the whole function f of x, those, one appears in the other, so we can subtract those are gone. Which, if you remember, that was good when this happened when we were dealing with the area of a square, because that meant that every single term that remained in the numerator had an h in it, at least one. And that when we had one had an h and one had an h squared. And same thing happened when we had our volume of a sphere. We had an h and an h squared and an h cubed in the terms that remained in the numerator, which that's good because with this polynomial structure, which is what we have when we have whole number powers, that means that every single term has an h. We can factor this out and reduce. So if I factor out h's from each of these terms, I have one fewer h than I used to. The first one only had one h factor in it. The next term had 2, and so forth up to the last term, which would have n factors of h in it. The last term is simply h to the n power. If I factor out 1, I can cancel out, and let me just circle something here. I can cancel out this h with that denominator, and notice that this first term doesn't have any h's in it, but every single other term does. The term right after it has one fewer power of h, so just be 1, and so on down the line. All the other remaining terms have h's in them. So looking at this last expression here, when I've canceled out those h's, there are h's that remain. And the reason we're concerned about the h's is because this isn't an approximate rate of change if h is any old thing. I want to form an exact rate of change. I want h to be essentially 0. By having it out of the denominator, that's good, because I don't like to try to imagine division by things that are essentially 0. at least when I have a compound numerator like this. When the numerator was 0, like it was for a constant function, that's fine, because I know 0 over something that isn't 0, that's 0 all the time. We're not so lucky here, but if each of these terms that remain, with the exception of the very first one, contain at least one factor of h, that means as h becomes essentially 0, I can make it as small as I want. It can overcome whatever other numbers might be in here, and that will make each of these terms, let me just get this out of the way, make each of the terms beyond the first one essentially 0 by multiplying on something that's essentially 0 and as close to 0 as I want. So that means that, and let me just scoot this out of the way for a moment, this rate of change rule for a function of the form x to the n is that the rate of change can be given by n times x to the n minus 1 when I imagine h to be small. So h essentially 0, h the limit as h approaches 0, imagine h extremely close to 0, whatever phrase you want to use, working from this f of x equals x to the n to find its rate of change function algebraically, we can see that this becomes something of the form, because all the rest of these terms have h's in them, so they're all as factors, so they're all essentially 0. Some closer to 0 than others because they have lots of h's. But in any case, this first term, n x to the n minus 1, is what remains as not multiplied by 0. And so that's our rate of change function rule that we're going to use for polynomial functions. And it also applies to any other power function. As I said, we'll prove it for other powers also, other than just whole number powers. But this n x to the n minus 1 for a power function, or sums or differences of these power functions, polynomials or otherwise, we just can use this rule of, well, I've got a coefficient that didn't used to be there, which is the number that used to be the exponent. And why I say used to be is because the exponent becomes 1 smaller. And we've seen this already. Again, when we had f of x equals x squared, we had the rate of change of that given by the function 2x. And we didn't write this, but that's first power. So you can see this 2 here in the spot where the n was. In the end, we have a coefficient that's 2, what the old exponent was, and our exponent becomes 1 lower. Or when we're dealing with our sphere, I'll just write the x cubed part of it. When we had the sphere, there was the 4/3 pi part, but we ended up with an x squared. It reduced in the end to 4 pi x squared, but it was 4/3 pi times 3x squared. So if I have something like h of x equals x to the 17th power, I don't have to worry about expanding x plus h to the 17th power and getting all the coefficients and subtracting and dividing and all that, because we've done that in general. We know that if I have a whole number power here, and it actually works with other powers as well, if I have a whole number power here, this h prime of x, the rate of change of this x to the 17th, will have a coefficient that's 17 times as large, and x is going to be to the 16th power. We know it's going to work out that way. You could go through it if you really feel like it with the whole x plus h expansion, but I bet you'll get bored with that real soon. The only interesting part comes from that second term of the binomial expansion, which would have started with this 17x to the 16th times a single power of h, and then factor it out and divide, and this is the only thing left. Now, what if I had something like j of x equals 32x to the 5th. What on earth do I do with that 32? Does that mean that when I take the derivative, I have to have something like 31 in the exponent, or? No, this is just a constant multiple. So I can kind of ignore the 32, not really do anything with it other than in the end, I'm going to multiply it back on. It's a constant multiple. If I want to take the derivative of a constant multiple of x to the 5th, then I worry about taking the derivative of x to the 5th. I'm not going to worry too much, because it's pretty easy. And then I'm going to multiply that 32 back on. Because we have our constant multiple rule, if I have c times an easier function, the derivative is c times the derivative of the rest of this. So it was c times f of x, and g of x was equal to that. But in any case, just if you have a constant multiple, just multiply it back on. So whatever 32 times 5 is, 160, x to the 4th. So this one rate of change function rule lets us deal with all sorts of powers of x. And I know that you talked about some of the algebra of this in recitations, but just as a further example, if I had something like, g of x equals 1 over x to the 7th power, how could I express g of x as a power function? Yeah, it's the same as x to the negative 7th. So if I rewrite it in that form, now the proof that we did was only for whole numbers, but I'm going to tell you, just believe me for now and we'll see it later, it works for other powers of x as well. And so following the same rule, if I wanted to find the rate of change of function g, and I've just been using this prime notation because it's really fast to write, but remember that this is the same as the rate of change of function g, or the rate of change with respect to x of function g. Regardless of which I call this, all of these, well, according to this rule, I'm going to write the coefficient is whatever the old exponent was. There isn't another one to multiply on here. And then what's the new exponent on x going to be? Negative 8. Yeah, be careful with the negatives. We're going to decrease the exponent by 1, so it's negative 7. We'll make it more negative. So negative 8th power. Or if I had something like h of x equals the square root of x, how could I write square root of x as a power function? X to the what power? 1/2. All right, so according to, oops, not 1/2 altogether. X to the 1/2 power. So if this power rule still applies, and we'll actually prove this one next class, that means that the derivative of this, regardless of what notation I use, is going to be 1/2. Old exponent becomes new coefficient factor, times x to 1 lower power. What's 1 less than positive 1/2? Negative 1/2. All right, so we'd have this, which, by the way, if you wanted to put that back into radical form instead of power function form, remember that this is 1/2 and then a negative 1/2 power. Positive half power indicates a square root. Negative half power indicates a square root in the denominator. So if you wanted to, we could write this as 1 over 2 times the square root of x. Don't worry about rationalizing denominators, by the way. That's a thing that's kind of important in certain algebra structures, but this is, we're just creating a function. We're not needed to evaluate this and deal with division by radicals. So in any case, I hope that was sort of helpful in our journey towards knowing some derivative shortcut rules, rate of change shortcut rules. There will be a take-home quiz over this weekend, but not a quiz in class on Friday. Yes. Either way, yeah.